Welcome back, chemistry students. This is Dr. Tullis. In this section, you will be able to calculate the change in entropy for a system, its surroundings, and the universe to determine whether a process is spontaneous under standard conditions and recognize how reaction conditions influence whether a reaction is spontaneous. The standard entropy change for the system in a physical or chemical change can be either positive, like the evaporation of ethanol. Evaporation is going from a liquid to a gas, and that means it's becoming more disorganized, so that would be a positive value. Or it can be negative, the synthesis of ammonia from nitrogen and hydrogen. If I have nitrogen gas and hydrogen gas to make ammonia, I have 4 moles of reactants and 2 moles of products. That would be a negative entropy change. How does this information contribute to determine the spontaneity of the process? Well, spontaneity is determined by the second law of thermodynamics, which states that a spontaneous process is one that results in an increase of entropy in the universe. The universe has 2 parts, the system and its surroundings. And so the entropy change for the universe is the sum of the entropy changes for the system and for the surroundings. So we can write this as our entropy for the universe is equal to the entropy for the system plus the entropy for the surroundings. We will now have to determine how the change being studied affects the entropy of the surroundings. If I have an entropy for the universe that's greater than 0, we have a spontaneous process. If it's less than 0, it's non-spontaneous. And if it is 0, then we are at equilibrium. As an example of the determination of a reaction spontaneity, let's calculate the entropy change for the universe for the reaction currently used to manufacture ethanol. Here is our reaction. I have carbon monoxide plus hydrogen gas to make ethanol. When we look at our thermodynamic values given in Appendix L, I would look up carbon monoxide to be given this value, hydrogen's value is that, and liquid ethanol is 127.2. So to find the system, we again do our products minus our reactants. So after plugging those values in, I got an entropy change for the system as negative 331.9 joules per Kelvin mole. A decrease in entropy for the system is expected because we went from having 3 moles of gas reactants, 1 plus 2 is 3, to 1 mole of liquid product. So 3 moles to 1, we had a decrease of moles. We also went from gas reactants to liquid products. So in 2 ways we can see that the entropy of the system should be negative. But let's look at the entropy for the surroundings. Recall that for a reversible change, delta S is equal to Q divided by T. Now under constant pressure conditions and assuming that it's a reversible process, the entropy change in the surroundings results from the fact that enthalpy change for the reaction, where Q is equal to H, affects the surroundings. So to find the entropy for the surroundings, it needs to be the opposite, or the negative, enthalpy divided by temperature. So we're going to look at that same reaction, but look at those enthalpy values and plug it in to find the delta H. So we're going to do products minus reactants. This is the delta H value for liquid ethanol. This is the delta H value for carbon monoxide. That's the delta H value for hydrogen gas. Plugging that in, I got a delta H of negative 127.9. Check those values to make sure that you can find them in the thermodynamic data appendix. So in order to find the entropy for the surroundings, because this is the enthalpy change for the system, therefore the surroundings is going to be the opposite of that. So I'm going to type in negative and then the value of delta H divided by T. Remember that S units is in joules per Kelvin mole. This is in kilojoules, so I multiplied by 1,000. You could have done that right up here before you plugged it in. That's fine. Do the math, and we should get an enthalpy for the surroundings of 429.2 joules per Kelvin mole. The last piece is to find delta S universe, so we're going to take our entropy for the system and add the entropy for the surroundings. This is from the first page where I took my entropy data for the system and did products minus reactants. The surroundings is when I did negative delta H divided by T. And I should get an overall delta S for the universe of positive 97.3 joules per Kelvin. This positive value indicates an increase in the entropy of the universe. And it follows the second law of thermodynamics that this reaction is spontaneous under standard conditions. Let's do a whole problem together. We want to find the delta S, the entropy of the universe, for the process of dissolving sodium chloride in water at 298 Kelvin. Well, if I'm dissolving, I'm taking a solid and it's turning into an aqueous solution. We know to find the universe entropy, I need to find the system and the surroundings. Let's do the system first. You need to look in the appendix to find those entropy values. Products minus reactants. There's 1 mole of products, and if we look up NaCl aqueous form, I have an entropy value of 115.5. Minus sodium chloride in solid form has a value of 72.11. So products minus reactants, I have an entropy for the system of 43.39 joules per Kelvin mole. That's a positive value. It makes sense. I'm going from a solid to aqueous, so solid to liquid. That is a positive entropy change. Now let's do the surroundings. We know the surroundings is negative delta H divided by T. We have to find the delta H first. So we need to look at our thermodynamic data and find the delta H for sodium chloride in aqueous form and sodium chloride in solid form and do products minus reactants. Check these values to see if you can find the aqueous delta H is negative 407.27 and the solid delta H is negative 411.12. When I do products minus reactants, I got a value of positive 3.85 kilojoules per mole. To then find the entropy of the surroundings, I need to take that delta H, find the negative of that, and divide it by that temperature. The standard temperature is 298 Kelvin. So negative 3.85, I need to times it by 1,000 and divide it by 298. I got a surroundings value of negative 12.92 joules per Kelvin mole. Now I can just add them together. 43.39 from step 1, negative 12.92 from step 2 gives me a value of plus 30.5. That means that the delta S of the universe is a positive value. It is spontaneous. Also notice that the spontaneity results from the delta S of the system, not the surroundings. We could guess by right here, the positive value for the system, that it would be a spontaneous process, not from the surroundings. This system entropy is where we can make that assumption that it will be a spontaneous process. Why don't you pause here and predict the spontaneity of the reaction of hydrogen and chlorine to give hydrogen chloride in this reaction. Find the delta S of the universe to verify that prediction. Pause here and look at your thermodynamic data to plug in. Let's see how you did. To find the entropy of the system, I needed to look up the values, the S values for hydrogen, for chlorine, and for hydrogen chloride, all in gas form. My product, HCl's value was 186.2, and I needed to multiply it by 2. So that's my products. My reactants, hydrogen and my chlorine, I took those values and I only multiplied them by 1. That gave me a value of 18.6, which is a positive value. So the delta S of my system is greater than 0. It's favored to be spontaneous since it's a positive value. Let's look at the surroundings. Our surroundings, remember, is negative delta H divided by T. So we got to find delta H. Look up the delta H for those 3, plug them in, and I got negative 184.62 kilojoules per mole. If you recall, a negative enthalpy is also favored to be spontaneous. Let's continue solving for the delta S of the surroundings by finding the negative delta H divided by temperature. Again, I needed to be in joules, so I times it by 1,000, and I got 619.219. Add those two together to get our delta S of the universe, and I got 637.8, which is a positive value. It is therefore spontaneous under standard conditions. But what if We found that delta S for the universe was positive for those last two examples. But does that mean that the reaction will proceed spontaneously all the way from reactants to products? No. The reaction will be spontaneous only to the point at which it is at equilibrium. When it is positive, the equilibrium position will be closer to the products than to the reactants. We say that it is product favored at equilibrium. What if our delta S for the universe had a negative value? The conclusion would be that the reaction completely converting reactants in their standard states into products in their standard states is not spontaneous. Does that mean that the reaction does not proceed at all? No. If we start with just pure reactants, the reaction will proceed spontaneously until it reaches equilibrium. But the equilibrium position will now be closer to the reactants than to the products. And then we say that the reaction is reactant favored at equilibrium. In the examples that we've just looked at, predictions about the spontaneity of a process under standard conditions were made using the values of the entropy of the system and the enthalpy of the system, looking to see if they were positive or negative values. There are actually 4 possible outcomes when these two quantities are paired. We can have an exothermic or a negative delta H and a positive entropy, both for the systems, and it would be spontaneous at all temperatures, so the delta S of the universe would be greater than 0. We could have an exothermic reaction, so another negative delta H, and a negative entropy. It depends on the magnitudes of enthalpy and entropy for these two values, but it would be spontaneous at lower temperatures. I could have a positive delta H and a positive delta S. Again, it would depend on the magnitudes of enthalpy and entropy, but it would be spontaneous at higher temperatures. And we could have a endothermic or a positive delta H and a negative delta S, and it would not be spontaneous at any temperature. Temperature plays a role in spontaneity. What condition causes ice to melt? Well, for my solid water to turn to liquid water, which is melting, I need temperature to be greater than its freezing point. So temperature is important here. What about if I need ice to freeze? If I need to go from liquid water to solid water, I need temperature to be less than 0 degrees. So notice going from solid to a liquid, my delta S is positive, but I need a higher temperature for that to be spontaneous. And here I have liquid to solid, so my delta S is negative, but I need a lower temperature in order for that to happen. So in summary, reactions tend to be spontaneous when I have a negative delta H, meaning that it's an exothermic reaction, and when I have a positive delta S, which means I'm going from low S to a higher S, or going from order to disorder. Or, as the second law states, a spontaneous process is one that results in an increase of entropy in the universe.